Hi. Can I just say, recording in this sunlight is fantastic, and I should try and do it more often. We're going to keep talking about ionic bonding and ionic compounds, but hopefully we're going to shorten things up a little bit in terms of the process of coming up with the formulas and the Lewis structures. So as a review of yesterday, there's a link to the reference table. You might need it, but I think I've copied the important information from your periodic table. I want you to determine the Lewis structure and the chemical formula of the neutral ionic compound created between gallium and bromine. If you want to do this on your own in your notebooks, go ahead. You can hit the pause button and do it yourself, but I'm going to get started. Given the valence shell configurations, I'm going to write the Lewis structures for both gallium and bromine. Gallium gets 3 electrons and bromine gets 7. I'm going to use X's to delimit them from the from the gallium. So as we start to transfer electrons, bromine can hold up to 8. Gallium has 3 to transfer, so we're going to need some more bromine. We can transfer our second electron, but then one more is needed to handle the third. So in terms of cleaning this up, we're going to end up with a gallium 3 plus ion, and then 3 bromide ions. Bromine ions, we're going to talk about naming them today. So one way to draw the Lewis structure for the compound is that. A second way would be to draw it like this. And the chemical formula would be GaBr with a subscript of 3. So there's your three different answers that you can have from this. But that process, 1, takes a while, and 2, we don't actually have a name for this chemical compound, so that's what we're going to talk about today. For quickly figuring out the chemical formula of your ionic compound, we have something called the swap rule. Notice that I'm not putting quotation marks on either the word swap or the word rule, which means this one is actually a rule, and it actually involves swapping. The idea is that if we can quickly determine the ion charges that are made, we can quickly determine what ratio of ions is needed to make a neutral ionic compound. Remember from the do now and from yesterday that if gallium is a 3 plus ion and bromine is a 1 minus ion, then you need 3 times as many bromines as you need galliums to make sure that the number of electrons transferred and that the sum of all charges stays constant. So really quickly to go through an example, all it says to do is we're going to write our symbols. We need to figure out the charges. In this case, the gallium is given, and the bromine, we have to think a bit. So you might want to look more at the bottom than at the top. The 3 electrons means we're going to get a plus 3. It's a metal, becomes positive. And for the bromines, they're going to become a minus 1. I'm going to put the 1 minus. I know I sometimes put just minus, but it's understood that, that 1 is there. And it's going to help us. What we do is we take the magnitude of the cation charge to be the anion subscript and vice versa. So this 3 swaps down to the bromines, and this 1 swaps down to the galliums, so that the formula we get matches what we saw on the previous slide. I'm going to go through this again with aluminum. Aluminum's in the same group as gallium, and it says plus 3 at the top. Sulfur's in group 16. It has 6 valence electrons. You're going to gain 2. It's a nonmetal. So we're going to take the numbers, not the charges, just the magnitudes, and swap them, and we will get Al2S3. This is a quick way to get from just elements to formula without having to draw the Lewis structures. Now, if you need to draw Lewis structures, a little bit more thoughts involved, but we'll end class with that. End the video. And then for magnesium oxide, magnesium's a group 2 element. Group 2s have a plus 2 charge. Oxygen's group 16, like sulfur, will end up with a 2 minus charge. When we swap these magnitudes, what we get, I'm going to write it over here, is Mg2O2. However, when it comes to ionic compound formulas, as a rule, we always reduce to show the simplest ratio of ions. So instead of 2 to 2, that can be reduced to be a 1 to 1, and so we're actually going to change that to MgO. If you had, say, a 2 to 4 ratio, that would become 1 to 2, and anything else that's similar. So there are your three examples. In terms of naming these compounds, there are a couple of more rules, some more conventions to use. First thing I should say is something that I've been doing the whole time. In terms of listing elements in a compound, typically, not always, we go in electronegativity order from low to high. This translates to saying metal first, non-metal second. Because non-metals always have higher electronegativities than metals. Always. I feel like I should put like an asterisk every time I say something that probably has an exception that I'm not thinking about. For the cations, either you keep the name the same or you change the ending to ium. Usually you just keep the name the same. And for the anions, we change the suffix to "ide." So we're not going to worry about the chemical formulas. I can copy them over from the previous slide if you want. But instead, we're just looking to develop the name, so I'm just going to write down the element names for each of these. And in each case, the ending will change to be "ide." It's not always 100% intuitive as to how those endings change, but for bromine, bromine becomes bromide. Sulfur, we drop the last few letters. It's not sulfuride. We actually go from sulfur to sulfide. So sulfur to sulfide. And bromine to bromide. And then finally, oxygen becomes oxide. So if you've ever heard that term before, if you ever heard the word oxide before, that means a bunch of things are being communicated to you. First, we're talking about an oxygen anion. You can refer to the cations and anions on their own. That's an oxide anion, a bromide anion. Or a lot of times using that term oxide conveys that there's a chemical compound present, whether or not it's being explicitly mentioned. And then finally, we can do this entire process backwards. If we're given a name, we can go back all the way to a formula or a Lewis structure. The only thing we have to remember is that when the swap rule is used, there's a reduction that takes place. So we can do a reverse swap rule, but that might be a little bit, going from a formula sometimes is a little bit dicey. So really quickly, I'm just going to do this all in reverse. Before we had the element symbol and we turned it to an ion and then a formula. So now we've got the name, we can kind of do that too. Instead of going from formula and name, we can go name to formula. This magnesium is a 2+, the oxygen is a 2-, and that would be Mg2O2, which reduces to MgO. Now when we're writing our Lewis structure, don't forget that the charge that we're putting is for the ion and not just the number, right? So in this case, even though our final formula has 1s, you have to remember that these are group 2 and group 16 elements, and we're getting 2s for our charges. So this is where it gets a little bit dicey. We write our formula. You can go from formula to Lewis structure if you're careful about what you're doing. So sodium is Na, carbon is C. Carbon has a lot of things listed on it, but if we're going by this convention that ide means negative, the number is a 4-. It has 4 valence electrons. It would gain 4 to fill up that second energy level before the third would go. And this is a 1+. So that yields a formula of Na4C, which means that we can speed things up by writing the coefficient 4, and then having our carbon with 8 valence electrons shown as our negative ion with a 4- charge. And then lithium nitride would be a lithium plus and an N group 15. That's 2,5. You want to go to 8. So that would be a -3. When you swap, you get Li3N, which means you should have 3 lithiums, each with a positive charge, and 1 nitrogen with its valence shell of 8 electrons and a 3- charge. So this whole idea, we should start developing a fluency of, if you have a chemical formula, you can come up with a name. If you have a name, you can come up with a chemical formula. you have a Lewis structure, you can go to a formula or a name, and these three different ways to refer to compounds, name, formula, and Lewis structure, we should start to develop some fluency moving forward. Thanks for watching.